This is the mold type. It has kind multiplicity multiplicity asterisk to asterisk. As I've said, we can regard every function as linear if it takes a multiplicity argument, and then we might think that every variable has this mult m type. I'd like now to talk a bit about what we can do with multiplicities. The multiplicity type is defined in GHC types, and it looks like this. Multiplicity is 1 or omega. I'm currently calling it omega, but this will likely change to many, so that is more intuitive. It turns out that when you use polymorphism, sometimes you have to use sometimes multiplicities will need some functions. For example, if we have multiplicity m here, if we have multiplicity n here, so let's suppose I'd like to pair two functions, like this is ampersand, ampersand, ampersand. This function will consume a m times, and this function will consume n m times. This function will consume a m times, and this function will consume n times. Right? So think about multiplicities not as 1 or omega, just numbers. So how many copies of a this function needs? Well, in this case, if this function is using, it needs m copies of a, and this function needs n copies of a, then you would need to supply m plus n copies. Right? So there is an so a pretty basic operation in Haskell, right? Tupling two functions, combining them, and we see a need for adding them. In the prototype, every time when addition is seen, we just replace it with omega, because 1 plus 1 is already omega. If I compose two functions, I compose b to c and a to b. If this function is using m times and this function is using n times, how many times does this a is needed?
M times n.
Right? M times n. Because let's suppose this function is making a list of 10 a's, so it's like replicate 10, and if I compose it with replicate 5, then I get replicate 50 effectively. Right? Okay. And if I have if I have the either function, which is a to m b, a to n c, so a to m b c, b n c, and I'd like an either a b, what should be the multiplicity here? Yeah, the maximum. So I'll call it supremum, so that you can, if the two things are not comparable, then you can take the supremum of that. Right? So there are three operations on multiplicities you can have.
But maximum is equal to multiplication in one and
Right. So in the current prototype, we don't have any of those. We just statically evaluate, and we cannot. If we cannot statically evaluate, we just say omega. It is true that if you have just 1 and omega, then you don't need both. And if we introduced the product type, then we would also need infimum, but that's for another day. If we like to express this using the mold type, well, if you have a mold m, mold n of a, then this is like having so I have this a available for me n times.
n at m?
M times n. right? So this type expresses the fact that I have n copies of A, and if I compose it with multiplying that by m, I get this product. And if you had this function as a primitive, then you could write composition. Likewise, if I have mult m plus n, okay, then I can decompose that to mult ma, mult na, right? And if I have either mult ma, mult na, then I can get mult sub mna. Yes, multiplicity is always an upper bound in the sense that, well, depends on the multiplicity. If one is pretty specific, but in general you can think of multiplicity as an upper bound. For example, omega means as a set of allowed multiplicities. Omega means everything goes. 1 means we can only have, so omega is used in set theory to denote all natural numbers. So omega means 0, 1, 2, and so on. You can use it any times you like. And the multiplicity 1, you can think that it means only the set containing 1. And those functions, addition, multiplication, and supremum, would be operating on those sets.
For example, if you want to introduce affine types like 0 to 1, so does
oh yes, you can say affine equals 0, 1. Right? So this is only an intuition. This is not how things are implemented. The way things are implemented are those are abstract types, and they are specified by the families such as addition, multiplication, supremum, because the type checker needs to perform those operations when type checking. Okay, let's change topic. Suppose we'd like to implement zipping. So I have two lists, A, B. So how does zipping in Haskell work? So this is the normal zip function. Can I make it linear?
Use both from this package instead of product.
No, that's not enough.
Wouldn't you have to also return the leftover bits if they are?
Right, the problem is with the leftover bits. So if I say linear, then I will get errors, and those errors point out those two lines. If I remove those two lines and make the function partial, this is linear. Now there is a property here of linearity that in a sense we are preserving the elements. So this zipping function, while it's less defined, the presence of leftover bits is often it's often suspicious. It often means that somewhere you mismatch the lists. It's not that often you'd like to just cut it at the shorter list. Maybe if one list is infinite, then yeah, it would make sense to just use it as a way to number items on the list. But in general, this zipping function seems to be, like, I would say, the more principled way instead of just discarding the remains. If you consider zipping, if you consider the earlier partition function, which was we take a predicate and we split it, then the situation is similar here, that is linearity enforces you that you can always shuffle elements in a list, but you cannot destroy them or duplicate them. Another example is sorting. If I have a function, and yes, those two should return A, and this one should return A. if I have sorting, then the only thing that sorting can do is permute. It can only change the ordering of elements in the list. So we are getting more guarantees, kind of free theorems, than in nonlinear Haskell. We can enforce that the sorting function cannot have some cannot have some bugs, right? It still can be buggy, but not in a way that it will duplicate the list. Another trick you can do is say, I will drop leftovers of x, but if I do that, I must be nonlinear in the first argument, right? Let's suppose we have a linear function, a to b, and we'd like to convert it to a nonlinear function. Well, we just call it, right? That works, except I already written it previously. If I change the type signature to this one, well, it doesn't. What if I have an unrestricted function and I'd like it to be linear? So my implementation is guaranteed to be linear, but I cannot prove this fact. Maybe it's some external library I can change the source of.
Unsafe course.
Yes, you use unsafe course. However, there is a problem with unsafe course. A small problem. That works, but it's not fully satisfactory. Do you see what could be better?
Well, this one covers A to B, not function to function.
Oh, yeah, I obviously meant this one. Yeah, and we are getting some error because I meant this. But the thing is, this unsafe course is not linear, right? That part I'm not happy with. Right. So I would like a stronger conversion function, which takes a function that's available in a linear context and gives me the same function except it's linear, at my own risk. How would you do that? Remember, we have a very powerful weapon, unsafe course.
Convert.
Well, you can't use convert in the definitions of convert because that would be recursive. The function wouldn't terminate.
Did you use similar trick as with move?
You can do move only if you have movable constraint, and we don't have it here. Yeah, so this is a small puzzle. How would you do that?
Unsafe course of unsafe course.
Once again?
Unsafe course of unsafe course.
Yes.
Oh my god.
Right? So normal unsafe course is A to B, but we want to coerce this function to be, so the external unsafe coerce is converting this function to this function, right? Where A is the nonlinear function type and B is the linear function type.
So now
Yeah.
you can change the arrow and convert.
So now that works. Okay? And if you think about it, we can say ID.
This would fail at runtime. The other one would.
Well, if assuming the representation is the same, which is, and you won't be using it in a bad way, right? Like if you know your function is linear, but you can't prove it because it's only in a library, you can't control it. This is a legit way to do that. So to use unsafe coerce, you need to be very careful. Like you cannot convert unsafe for example, if you have two data types that have two Boolean data types, you cannot unsafe coerce between them. You might think that JSC implements it using tags or something, but nothing is guaranteed. Basically, you can unsafe coerce only if the two types are really equal, except you don't see it, the compiler doesn't see it, or you can unsafe coerce during any. The exact details are in the documentation.
So in case if you unsafe coerce a function that use the resource multiple times, would GAC error or would it silently fail?
Well, if your program compiles, then it will probably crash at runtime.
So it will still crash. It will not like actually use the resource twice.
It might use the resource twice. Point is, you are then doing undefined behavior, and the program can't do anything, right? Nasal demons. Okay. A different thing I like to show is, if I have a linear function, you might be under the impression that x must appear on the right hand side. Right? If I have a linear function, then x must appear here. Well, I wish there is one little exception that is not implanted here, and is this one. Okay, so this function is linear because all of its branches are linear. It just doesn't have branches. Right? If your pattern match on a Boolean, your function must be linear in true and false. Here we have 0 branches, so we are linear.
So why is in all branches? Why is used in all branches?
Every branch uses y linearly because there are no branches. Okay, what's next? I'd like to talk a bit about point free. Is this visible? Point free. Who has heard about point free? So point free is a tool that lets you remove lambdas and make a so a point is basically a lambda in this context. If you have a long expression, you don't like lambdas, you don't like naming things because people are bad at naming things, you can use point free to get a version which contains no names. For example, if I say point free x of, let's say, x0, I get $0. Right? If I take 3 arguments and I say xzy, this is?
Identity.
No, they are different order.
Sorry.
Let's flip. Alright? And some other examples are possible. If I say xzy and then zy, maybe a singlet only somewhere, yy, z. Yeah, then you also got a pretty readable expression. Yeah. So it's a pretty effective way to, you see, it often abuses those ups and flips and ideas. How does this thing work? And does it always work? And if you give it a linear function, will it give a linear expression? The answer is yes. So, how point free works? And I will use only the simple part of Haskell, which contains lambdas, variables, and application. If we'd like, so if there are no lambdas, there is no problem. We just return the output as is. If there is a lambda, we can look at the innermost lambda, one which does not contain any lambda. So let's suppose I have lambda x to 0. How would you translate this? That's const 0. Great. What if I have lambda x to x? This is ID. If I have lambda x to y, where y is some different variable than x, this is const y. If I have a lambda and there is a lambda there, well, I'm looking only at the innermost lambdas, so this case cannot happen. So the only remaining thing is when I have an expression, some f of y here. So what we need to do is, ideally we would like to run this translation recursively. You can think that this x is some kind of environment, and we'd like to thread it to both f and y. And Haskell has a combinator for that. It's in the applicative class, it's up. And that works. So what up is doing, if you say up f, z, sorry, fc yc. What up is doing is it's passing this x as an argument twice. So if I'm getting this x, if x comes from here, it will be passed both to f, because now f takes x, and to y. And this translation always works. It's actually the functor applicative. This is the pure in applicative, and this is lift a. This is the asterisk operator, greater than, smaller than, asterisk, greater than. However, the problem with this, and this translation works. However, the problem is that it's not linear. In fact, there are two problems. Const is not linear, and up is not linear. So how do we fix it? Let's suppose we now have a linear lambda. How would you translate this expression? If y is a constant different than x.
Then it's not linear.
Right, so impossible. X, well, this one is easy. Now, if we have an application,
Why can't you use const for that also and just pass
the point here is that we are assuming now the lambdas are linear, and we'd like to get a linear term as an output. So if you use const, it won't be linear.
Oh.
Right? Const is linear in the first argument, but this is a situation where we already applied the first argument, so the resulting function is not linear. We will need linearity in the second argument. Okay, what if we have an application?
Can we move the x to both?
Yeah, so the problem is that previously both f and y could use x. And that was the source of the problem, because up is passing x to both of those. And now we can't do that anymore. But since we know that those terms are linear, there are only two cases. Maybe x is here, and maybe x is here, right?
Yeah.
How would you translate this one?
Using additive product.
Hmm?
Using additive product.
No, there are no products here. Like I have a Haskell function lambda x sin of something. How would you translate it? How would you simplify it?
Using flips, push to the right and then eliminate.
Yes. So this one is just composition of f with whatever is remaining, right? So I can translate this to sin dot lambda x something. On the other hand, here this x is inside, so I need to flip. So I can translate this term to flip of y, and then do this, and then I'm back at this case. Okay. Now, linearity is introducing, as you see, we started with const and up and id, and those are called ski. K is const, s is up, and I is id. And this is the ski combinators. This is b equals composition, c is flip, and I is id. So in a sense, if you can write any linear term using only those functions. If you introduce application, the up combinator, then you are no longer linear. So if you don't understand the rules regarding the regarding lambdas, there is a different definition of linearity. Those are programs that you can write using those combinators. If you'd like to add duplication to that, if you'd like to add duplication to that, you can add a different combinator, the joint function. This one. So this is a way to explicitly double an argument. If you'd like to add discarding of arguments, like in affine logic, then you can add const. So this is a different way of looking at what programs are linear or affine, using only those combinators. Now you might wonder, can we remove anything from here? And it turns out we can remove flip. We can say that programs cannot change the order of type of arguments. So I would be able to write a function which takes a tuple and returns a tuple, but I couldn't do it this way. That would be not allowed, because I would be flipping something. So while linearity allows you to shuffle things around, this more restricted system would only let you to preserve the order. In linearity, if you have a function that takes two lists and returns a list, it must return a permutation of the sum of the two lists. If you enforce ordering, if you don't allow flipping, then this function, by its type, must concatenate. There is nothing more it can do. So the intuition you might have is if you have allocate memory on stack. You put something on stack, and now you can only pop it off. So this, if you have a stack, you can't flip two things around. You would need a separate primitive. Okay, now for something different. Can you give me an example of a function that is not completely obvious, that has this type? By the obvious, I mean you could just return an empty list, and I don't want to do that.
I can map some list of integers.
Yes, so I can say f10, f20, f30, right? It turns out that this is the only thing you can do. So any function that has this type, and it doesn't throw an exception or a loop or anything like that, must be mapping of a function that is given as an argument to a fixed list of integers. In other words, this type is equivalent to the list to a list of integers. This is called the unit lemma, by the way. Basically, because we have to return an A, the only way to get an arbitrary polymorphic A is by calling this function. And to call this function, you need to provide an integer, and you have to do that in every element to every element of the list. What I'm after is a linear types twist to this idea. What I would say is, how would a function, I'm giving you still a function, but this time I'm also giving you a linear argument a. What could be there? No. So I could put an x, and then I would have to give a different list, right? And this x doesn't have to be first. Right? I could write it this way. So, well, this is a list. This is a list, but not quite. It is a list with one element removed, with one element highlighted. This is called a zipper. So the general intuition you might have is that you have some container. Let's say you have a list, and you get the zipper type by saying, by taking this container and removing one element. You remember which element was highlighted, what was its position, but you don't no longer have an A inside. So if I'd like to have a zipper of A, what are the possibilities? So we have this tuple.
You've got three choices for what element.
I need to put this X, this hole somewhere.
Yeah.
So data like triple zipper is a new data type that you get from saying left. If it's left, then I still need to remember the middle and right element, and likewise for the other two. Okay. Now, if you haven't seen this idea earlier, there is a very interesting connection. Now, if you think about how many triples are there? How many triples are there? If let's say the type A has two elements, then there are 8, right? So this is A cubed. And how many elements are there in the zipper? 3A squared. What operation transforms A squared to A cubed to a 3A squared?
Derivative.
Is derivative, right? So we have a kind of derivative on top on types.
And that's how you get a zipper in general.
Yes. If you think about it, if you have a container that's an either, the only way to have a value that will have a hole somewhere is to either put the hole in the left or in the right version. If it's a tuple of two things, then the hole must be either in the left hand side, and then the right hand side is not changed, or it must be in the right hand side, and in this case the left hand side is not changed. So those are the laws that you might see in the calculus class of a derivative, right? And you can implement them as type families in Haskell. The nice things about and to implement this, you don't need linear types. But what I found nice is that when you have linear types, you can give a single uniform definition of what a zipper is. It's this type with that one little linear argument which enforces that the hole will be put in exactly one place. Just to be honest, this zipper representation, while it's nice, the normal way to do zipper lets you navigate through a structure. So if you have a left version, you can plug it, or you can move the middle element and so on. It's far trickier to do that with the linear types. So there is a downside. When I first learned what a derivative is, I didn't really learn it. I just learned the rules for how to compute a derivative. And to understand the concept of limit, I learned that much later. And I think when I first saw the zipper, I only knew those rules, but only with linear types I can say this is what a zipper means, right? Okay, now I have a topic of GHC internals. I will point at a specific issue that has not been resolved in the implementation, but I think it's pretty instructive. And let's start with GADT. This is a data type. You can construct it only when the two type arguments are the same. So it's evidence of equality of the two things. If I have this evidence, I can convert between the two types. Example. If I know that A is equal to B, then I can write a function from A to B. Convert mach x equals x. Okay. I have to pattern match on this mach x. Even though I'm given a value of type equal AB, I can use the equality that A is equal to B only when I pattern match on it. So if I say this, I'm getting a type error. How does GHC do this internally? It was a pretty large breakthrough to systematize the treatment of GATs in Haskell. The way this works is that this mach x type, mach x value, is getting an extra parameter. It's called a coercion. That coercion is evidence that the two arguments are equal. You do not write coercions in Haskell. What you write, you implicitly use them. Let me show this. Do I have it here? Yes. So this is a program, and this is our function. This is called core. This is how GHC internally represents Haskell. So Haskell is compiled to this version, which is explicitly typed, and on this version, optimizations are performed. Core is much smaller than Haskell. It has only 7 or so constructors. So while normal Haskell is type classes, deriving, let, where, view patterns, add patterns, there are many ways to do the same thing. Core is extremely simple. If you just modify the surface syntax but you do not touch core, what you are doing is you are introducing syntactic sugar to Haskell. You are adding a new way of doing things that already exist. If you modify core, it means the language changes in an essential way. It means you not only have to change the surface syntax, but all optimizations must be compatible with the change, and so on. This is why linear types is such large. We are not just changing what you write in Haskell, we are changing what is compiled to, so that all optimizations can preserve linearity and so on. Now, if you look at this mach x, there is an extra argument that was not present here. Here does not take any arguments, but in core it does. And this is the coercion. Now you need to explicitly use the coercion. If we know that A is equal to B, previously we could just say X. But GHC elaborates this to saying X, well, but X has this type A and you want type B, so what we do is we cast X using this coercion. And so far so good? Now this program caused us some pain. This program is a data type with two constructors, a GAT, 1 and omega. And notice this is a conditionally linear function. We take a T of M and we pattern match on T of M. If it's 1, then we learn that M is 1, therefore we have to be linear. If it's omega, then we don't have to be linear. So this is a way you can combine linearity and GATs. And this is it's not obvious how it should work. Coercions are done on types. You have an expression of one type, you have a coercion, and now you can cast that expression to a different type. What we would need here is probably some form of saying you have an expression of that multiplicity. You know this multiplicity M is equal to omega. Therefore, you have an expression whose multiplicity is omega. We don't have that yet, and this is one of the reasons why error messages are so poor, effectively. But I think it's pretty interesting to know about coercions. This took quite some time to develop, and I would say is a reason why Haskell is so robust and has survived so many years. The language is really huge. There are so many ways to do it, and core is the reason why GHC is sane. In that sense that there are only a few things you can do. If you try to write an optimization, you don't need to think about all the extensions. You just think about a simple data type. With so many constructors. It's either a variable or literal or application. There are no type classes. The only way, there is no if because there is only case and so on. Yes, I made this little diagram showing dependencies of GHC features. And it turns out that if I think about it, linear types would not be possible without earlier breakthroughs in GHC. So we use polykines because we want multiplicity polymorphism, and multiplicity is a kind. We use data kinds because we want to say data multiplicity equals 1 or omega. We use levity polymorphism not directly, but the implementation of levity polymorphism and linear polymorphism is pretty similar. We use pattern synonyms for backwards compatibility. And type families are things like addition and multiplication. And those features were in part built on top of other features. And this makes me think what people will build on top of linear types. I don't know that yet. But the technology tree of Haskell is pretty complicated. And that makes me happy that we are not just adding one feature and another feature, but we are actually building on top of each other and using things that are now available, that previously weren't.